Hi class, I just wanted to do a little video to cover some of the concepts surrounding the concepts of energy and work, which we've been studying in class for the last week or so. So as you know, we've been studying what we call mechanical energy. So this is part of the overall concept of energy that we encounter in physics all the time, but it is very specifically related to the things that you and I have been discussing, which is energy associated with motion, and now as we move onward, energy associated with forces in particular. And so you'll recall that we had defined there was a type of energy that we are accounting for that we call the kinetic energy. And kinetic energy is the energy that an object has as a consequence of it being in motion. So kinetic energy, the formula that we use for it is 1/2 times the mass of the object times the speed of the object squared, or the magnitude of the velocity squared. So if the object is not in motion, it has no kinetic energy. If it is in motion, then it certainly has kinetic energy. Now, the concept of forces come into here, into the discussion of energy in two different ways. And that's because we have roughly two different kinds of forces that we're interested in when we discuss energy. The first of them is something called a conservative force. So conservative forces are forces that, as a consequence of their action, they have the ability to store energy in a system. That is, it is energy that if we store it in a system, we can get it back out without any losses. The other kinds of forces that we're interested in are so-called dissipative forces. And dissipative forces also can change the energy of a system, but all they really do is they remove energy. Okay, and so these systems, if you try and exert them on a system, the energy is not maintained, it's lost, it's not stored in any way. Okay, and the classic example of a conservative force is gravity, which we've been discussing, and the classic example of a dissipative force is friction, which we'll talk about here in a moment. Okay, so how does this all relate to this concept of work? So the whole notion of work is that work is a concept that lets you talk about how energy is exchanged with an object. Okay, so work is energy, but it's energy exchanged with an object when a force acts over a distance. Okay, so the kind of classic example of this is if I am pushing on a box. Okay, so I'm exerting a force on the box, and as a consequence of me exerting a force on the box moves across the floor. So I say, I worked on the box. I did work because I pushed on it and I caused the box to enter a state of motion, which it wasn't in before. In the same time, the box was moving, but then when I'm all done, when the box gets over here and I stop pushing on it, the box is not in motion. And so there was another force at work here, and that is the force of friction between the box and the floor. And so we say that the friction dissipated the energy that the box had. Friction also did work on the box. There's another case, okay, and this is a case where if I take a box and I were to lift it up over my head, then the action of lifting the box up from the floor over my head, I also do work. I worked on the box and I lifted it up, and as a consequence of that, the box is in a different state than it was before. In fact, when the box is over my head, there is energy stored in the box. How do I know there's energy stored in the box? Well, because if I let go of it, the box falls, and by the time it heads down towards the ground, it has kinetic energy, which it did not have when it was held over my head. Okay, and so what we want to understand is we want to understand the differences and what's going on between these two cases. In particular, there are multiple forces acting on both of these. In this case, there's the force of me pushing and also the force of friction. In this case, there's the force of me lifting and also gravity. In both cases, all those forces do work. Energy is exchanged, it's somehow put into or extracted from the box, and what we'd like to understand is the differences between those. Okay? Okay. So the way we started thinking about that, and I think the easiest way to think about it, is to go back to the example of potential energy, which we used to convince ourselves that forces were in fact involved in this whole game. You'll remember that the definition of potential energy is that the potential energy is equal to the mass times the acceleration due to gravity times the height through which an object is raised above the place where the potential energy is zero. And I factored it the day we introduced this in this way because this is the displacement. And this is very clearly the force, what you and I have been calling the weight force or the gravitational force between the mass, the book, whatever it is you're lifting, and the Earth. Now, this formula is an expression of energy, but what it does is dimensionally, it shows us that energy, and in this case what we're trying to explain, work, can be related to forces and displacements. And so the generic formula for work, which is a scalar, okay, so work, we'll give it the capital symbol capital W, it's a scalar. A scalar is defined by this vector multiplication that we call the dot product. Okay, and there's a mathematical operation for how to compute the dot product if you know some things about the vectors. But for our purposes, we're only ever going to want to know what is the scalar value of the work. Okay, and so we're going to evaluate this dot product, and the way we'll evaluate it is we'll take the magnitude of the force vector, okay, represented by the absolute values of the force, times the magnitude of the displacement vector, represented by the absolute value signs around the displacement vector, times the cosine of theta, okay, where this angle is the angle between the force vector and the displacement vector. Okay, and this is the angle that we've been talking about and we've been wondering about because this angle is in fact the angle that plays a very prominent role on telling us whether or not the work is positive or whether or not the work is negative. Okay, so remember we said that work is the exchange of energy with an object. And that word exchange is really important because it tells us whether or not energy is going into or going out of the system. Okay? So what we define is when we say the work is positive, then energy is going into the system. And similarly, when the work is negative, then we say that energy is going out or being extracted. Okay, so that definition then, if I use it in tandem with our definition of work up here, what we can do is we can look at under what conditions is energy being put into a system by a force, or under what conditions is energy being taken out of a system by a force. Okay, so let's do that, okay, and let's think about our specific examples that we've been talking about up to this point. Okay, let's imagine the case of me either lifting the box up or the case of me pushing the box across the floor. Okay, so the work in that case, I claim, is positive, is equal to the magnitude of the force times the total distance that I either push the box or the total distance that I lift the box. Okay, so, and the positive comes from the fact that the angle in both of those problems is 0. So let's think about me pushing the box across the floor. Okay, so if I were to go back to my picture of me pushing the box, okay, so the box has a force that I am exerting on it in that direction. I'm pushing the box across the floor. Okay, and then the box is moving from wherever I started to wherever I end. Okay, and so in the same way, the displacement points from the left to the right. Okay, so the angle between the direction that F points and the angle between the direction that the displacement points is in fact 0 degrees. And so the cosine of theta is the cosine of 0 degrees, which is +1. So the absolute value of the force, whatever it is, the absolute value of the displacement, whatever it is, times +1 gives me a positive force. Okay? So in this case, I put energy into the system when force is in the same direction as the displacement. Okay? Now, there's another force involved here, okay, and that is when the box is sliding, I'm pushing it across the floor, but friction is acting against me. Okay, so in this case, I might ask, up here, I would have called this the work that I did on the box. Okay, I could similarly ask, what is the work that friction does on the box? And in this case, I claim that it's minus the value of the frictional force, whatever it is, times the displacement. And by a very similar argument, if I go up here to my diagram, the friction points in this direction. So in that case, the angle between the force vector and the friction vector, the force involved, sorry, let me say that again. The friction vector is the force vector, and the angle between the friction vector and the displacement vector is 180 degrees. Okay, and so the cosine of 180 degrees is -1, and that's where that minus sign in the work done by the friction on the box actually comes from. Okay? So in that case, energy is removed from the box. And in this case, friction, the force is in the opposite direction as the displacement. Okay? Okay. Now, this leads us to an interesting concept that we have in physics, which is there's all kinds of forces acting on an object at the same time. And as a consequence of all those forces acting on an object, its energy is changing and changing continuously. Okay, so we have this idea called the Work-Energy Theorem. Okay, and simply stated, the Work-Energy Theorem, it tells us what happens to the energy of an object as a consequence of all the forces acting on it. Okay, and so simply stated, the Work-Energy Theorem says that the net work done on an object, that is the total sum of all the energy put into the object and the total sum of all the energy put out of the object together, the net work done on an object is equal to the change in the kinetic energy of the object. So if I write that mathematically, I say that the net work, which is the sum of all the works on an object, is equal to the change in the kinetic energy of that object. Okay, so let's go to the case of, back to the case we just did of me pushing the box across the floor. Okay, so I was here, and it's really hard to draw a person with their feet pushing a box. Okay, so I'm pushing the box across the floor. So this is the force of me on the box. There is a force of friction of the floor on the box. Okay, and the overall distance that the box travels is some displacement delta x. Okay, so in this case, the net work, okay, the sum of the work done by this force plus the work done by this force is equal to the, as we computed on the last page, the force that I exert on the box times the displacement plus the work that friction did on the box, the force of friction, times the displacement, and that's equal to the total change in kinetic energy in the box. Okay, so before the problem starts, the box is not moving. When I'm all done, the box is also not moving. So in the end, the kinetic energy doesn't change at all. The box starts with no kinetic energy and it ends with no kinetic energy. And so what that means is that the work done by me to push the box across the floor is exactly the same as the work done by friction to stop the box moving across the floor. Okay? So this is an example of how we use the work-energy theorem, but I think there's an interesting and another cool example related to conservative forces that we should look at. Okay, so let's think about the case where I'm lifting the box or lifting the book over my head. Okay, so in that case, once again, we're going to ask what is the net work done as I take a book and I lift it over my head. Okay, so it's raised up off the floor, some displacement h. Okay, and what is the net work done on that book? Okay, well in that case, the net work is the work done by me to lift the book plus the work done by gravity as the book is being lifted. Okay, so let's look at that case in detail. So there's two forces acting on the book. If I draw the free body diagram, there's the force of me lifting the book, and while I am lifting it, there's the weight of the earth pulling down on the book. Okay, and in the diagram here, we show that the overall displacement, delta y, is this height h. Okay, so the angle between the force of me lifting the book up and the displacement is 0. So the work done by me is positive. Okay, so this is the work done by me lifting the book. Okay, and then the angle between the displacement and the acceleration, the force due to gravity is 180 degrees. So in that case, the work done by gravity is negative. Okay, so this is the work done by gravity. Okay, and the net work done has to be the sum of those two. I lift the book up, and then at the end of the problem, I'm holding it over my head. It's not moving, which means it doesn't have any kinetic energy. So this is in fact equal to 0. The book has no kinetic energy at the end of the lift. Okay, it started with no kinetic energy because it was sitting on the floor minding its own business before I picked it up. And then at the end, it has no kinetic energy when I stop. Okay, now let's think about a slightly different version of this problem, which is I start holding the book up over my head, okay, and then I drop it. Okay, and in that case, when I drop it, it falls to the ground. Okay, so here at the start, the kinetic energy is equal to 0. And at the end, right before it hits the ground, the kinetic energy is not equal to 0. Okay, so in that case, what does the work-energy theorem tell us? Well, it still gives us a consistent picture of what's going on in the problem. Okay, so let's once again use the work-energy theorem. The net work is the sum of all the forces on the book acting while the book is falling. Well, in this case, there's only gravity pulling the book down. Okay, so this is the weight of the Earth pulling the book down. In this case, the displacement is down. The book falls some height h. So this is the work done by gravity on the book. The force of gravity is just the mass times the acceleration. The displacement is h, and it is positive because the angle between the displacement and the angle between the force is 0. Cosine of 0 is positive 1. So in this case, the work is positive. Energy is put into the book. It had no kinetic energy at the start, and it definitely has kinetic energy at the end. Okay, and that energy came from the work done by the gravitational force. Now, you and I have typically, and indeed still can, solve this problem using the conservation of energy. Okay. What we might have done is we might have said the energy at the start of the problem, because we're dealing with conservative forces, must equal the energy at the end of the problem. So in this case, we might write the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy. And in this case, when the book starts at its initial height, it has no kinetic energy initially. It has mgh of potential energy initially. When it gets to the bottom, it has 0 potential energy at that moment right before it hits the ground, and it has some unknown final kinetic energy. Well, in fact, this tells us that the final kinetic energy is equal to mgh. Everything that was stored in potential energy has been converted into kinetic energy, which is the same result that we get using the work-energy theorem. So you might ask, quite reasonably, when is the work-energy theorem useful? Well, the work-energy theorem is really useful in cases where you have dissipative forces or forces which are not conservative. This is the case that you saw up here at the beginning, where I lifted the book. In this case, gravity and me were both doing work on the book. And so I was putting energy into the book, and in the absence of gravity, if there was no gravitational force, me pushing on the book would have given it kinetic energy. But gravity took all of that energy away from what would have been kinetic energy and stored it in potential energy. And so the only way to understand what I did to the book, the energy that I added to the system, is to look at the work that I exerted, that I did on the book as I was exerting a force on it. Okay? So this is what we've been trying to understand for the last couple of days. Hopefully it's a little bit clarifying here now. We'll use this to solve some problems and do a little bit of homework. And otherwise, I will see you all in class. Have a good day.